Hey guys, welcome to this explainer. Okay, I want you to imagine you're an architect, but instead of designing a physical city with roads and brick buildings, you're designing a digital one. Today, we're building a computer network from the absolute ground up. It's going to be fast, interactive, and honestly, it'll completely change how you look at the digital world around you. Let's dive right in. Here's our digital blueprint for today. We're going to cover the foundation, hardware blocks, network shapes, rules of traffic, the scalability pivot, and finally, keeping it safe.
All right, let's kick things off with Section 1, the foundation. We got to start small, right?
So, what exactly is a network at its core? Simply put, it's just a collection of computing devices connected to each other either by wires or completely wirelessly. It's all about connection, communication, and sharing data. Like whether it's your phone linking up to your home Wi-Fi or the entire computer lab at school, that connection right there, that's a network.
Now, we usually talk about two main sizes of networks. On the top here is a LAN, or local area network. This covers a pretty small geographic area, like a single school building, where you might all share access to one local server. But what if a company has offices on opposite sides of the entire country? Well, that's a WAN, or wide area network. WANs rely on external equipment from internet service providers to create this massive virtual link across cities or even countries. Pretty cool, right?
Moving on to Section 2, hardware blocks. Let's look at the actual physical parts that connect us.
You know, you can't build a house without bricks, and you definitely can't build a network without hardware. And every single piece has a highly specific job. A switch is kind of like a local traffic coordinator, connecting devices in a single room to form a wired LAN. A router, though, thinks a lot bigger. It connects different networks together, acting like a GPS to find the absolute fastest route for your data to reach the internet. Then there's the NIC, or Network Interface Card, which gives every device a unique MAC address so it can actually be identified. And lastly, the WAP, or Wireless Access Point, which beams out the Wi-Fi signal so we can connect without being glued to a wall.
Now that we have all our hardware, how do we actually arrange it? That brings us to Section 3, network shapes and understanding topologies. Okay, so a network topology is literally just the layout diagram of our hardware. This first shape is called a bus topology. It is essentially a single main cable, kind of like a one-lane highway, that all the desktop computers plug directly into. See those little circles at the ends? Those are super important. They're called terminators. They absorb the electronic signals so the data doesn't just hit the end of the wire, bounce back, and crash into other data. Next up, we have ring and star topologies. In a ring topology, which is the one on the top, data travels in a literal circle. It moves in just one direction, passing through each computer until it reaches its destination. But the star topology on the bottom, that is what modern networks really rely on today. Notice how every single device has its own dedicated cable connecting it directly to a central switch?
Let's weigh our options here. Imagine you're the lead engineer managing the budget for your school's network. Do you go with the bus topology? Well, it's super cheap and really easy to install because it hardly uses any cable. But the downside is a huge risk of data colliding, and if that one main cable breaks, the entire network goes totally dark. No way. Or do you choose the star topology? It's highly dependable. If one person's cable breaks, everyone else stays online perfectly fine. Plus, the switch directs data specifically, so there are zero data collisions. The catch? It requires way more cables, making it much more expensive to install. But honestly, for most engineers today, that reliability is for sure a cost worth paying.
All right, Section 4, rules of traffic. Let's check out protocols and packets.
Imagine the absolute chaos if a smartphone made by one company couldn't talk to a router made by a completely different company. The whole internet would just break down. That's why they must use a protocol. A protocol is an agreed set of rules that computers follow to communicate, totally regardless of who manufactured them. It's basically a universal digital language.
The absolute most important protocol to understand is TCP/IP. Think of it like trying to mail a heavy textbook to a friend. Instead of mailing the whole giant book at once, you tear out every single page, put each page in its own numbered envelope, and mail them all separately. Crazy, right? But here's how it works digitally. First, TCP breaks your data file into tiny units called packets. Second, IP adds the sender and receiver IP addresses, plus a packet number so things stay organized. Third, these packets are sent zooming across the network. And finally, the receiving computer checks the packet numbers to reassemble the data in perfect order.
Just follow the journey of those packets right here.
Look at how video packet 1 and video packet 2 don't even follow each other in a straight line. They take completely different paths, jumping through various routers. They act independently, constantly looking for the fastest possible route to avoid digital traffic jams. It is a wildly efficient way to move information. Okay, here is where things get really interesting. Section 5, the scalability pivot. How do we prepare for growth?
I've got a huge question for you. Imagine your school suddenly opens a new wing, and 100 new devices, like laptops, tablets, and phones, join your perfectly designed network overnight. More students, more devices, more pressure. So what happens? Will it still work? Well, if you haven't planned for it, your network will start buffering, lagging, and totally crashing.
That exact scenario is why we need scalability. Scalability simply means how well a network keeps working as it grows. It's the capacity to enlarge a network with more devices while ensuring it remains fit for purpose. A good network is built sustainably. That means we don't just build for today, we design a blueprint that is ready to grow without breaking tomorrow.
To grow smart, there are a few core factors we absolutely have to plan for. First is security. If a network gets unstable from too many users, firewalls can actually fail, leaving you wide open to cyber attacks. Second is storage solutions. More users mean generating way more files, so we have to upgrade our servers. And third is accessibility, which is all about bandwidth. Think of bandwidth like a highway. A few cars mean a smooth ride, but if you add hundreds of cars without widening the road, you get a massive traffic jam. As networks grow, we have to widen our digital highway with more bandwidth so devices don't just randomly drop offline.
Which leads us to our final part, Section 6, keeping it safe, defending the scaled network.
Okay, so we started with Office 1 on the left, but now we've scaled up and added a whole second office on the right. With this expansion, we have to deal with signal distance. The farther data travels across big buildings, the weaker the Wi-Fi or wired signal can become. So administrators have to carefully plan their budget, buying extra switches, repeaters, and powerful firewalls to accommodate the new traffic. Growth always costs money, so smart planning from the start prevents messy, expensive upgrades later on.
With millions of packets flying around this massive new network, things are bound to go wrong. Like, why do packets get corrupted? Well, an electrical spike or power surge can literally flip the binary zeros and ones in a data packet, causing a glaring error. Also, interference from nearby electrical waves can disrupt the signal. Hardware like our central switches can just fail and misroute data entirely. And of course, security breaches from hackers or malware can easily overload the system. Because of all this, networks must have built-in error checking to catch these problems and re-request any missing packets.
To fight back against those threats, network administrators layer on utility software as the final line of defense. They run virus scanning, schedule daily backups, and configure firewalls to block bad traffic. But honestly, perhaps the most important tool is encryption. Encryption actively scrambles our data so that if a hacker intercepts a packet, especially when users are connecting remotely from home, they can't understand a single word of it. It's a vital, invisible shield around our digital blueprint.
So, here is my final challenge to you. The next time you log on to the Wi-Fi at your school or even just look at the router blinking in your living room, think like an architect. Ask yourself, how will you design your next network to not just work today, but scale smoothly and safely for tomorrow? Remember, build smart, grow smooth. A scalable network is a future-ready network. Thank you so much for exploring this explainer with me today, and keep learning. See ya!